Okay, we're going to. I'm sorry. I do. They should, and I try to post them on the in the online classroom in Canvas. So if you miss a lecture, you should be able to. Hopefully, by the end of that day, it'll be on there, so you can just and go to YouTube. It takes you to YouTube where you can look at it. If any of you try to look at one of the lectures online on Canvas, when you click on that lecture, it'll bring you to a page and it'll probably put up a window, at least on my computer, it puts up a window that says YouTube refused to load the video or whatever. If you go click on the title at the top of the window, it'll open up YouTube in a separate window and it'll play the video.
That's what I did. I watched it last night. I just went to YouTube because it was
Yeah, if you just click the title, in fact, I think I wrote the title, click here if it doesn't load or something to that effect. Just click on the title, it'll load into a different window. Okay, we're going to take questions. We're going to look at any questions from the homework. Right now, the first one someone asked about is number 16. Talks about a large electroscope, two 21-gram spheres on 78-centimeter wires. So you Oh, I'm not going to work it for you. We're just going to look at the setup and see how to work it. And the angle is 26 degrees each. Now, it says here that we're going to consider that all of the charge that they're charged with resides on the spheres. And so we need to know what the charge is, the total charge. We know half of it's here and half of it's there. So what's the first thing we know about this? We can know immediately, we can find out this distance here. Going to be 2 times the cosine, 78 times the cosine of 26. And that's going to give you the distance between them. What total forces do we have acting on this? You know, gravity, 21 grams times 9.8 meters per second squared. How many newtons are pulling straight down on both of them? What can we write about the force between them? Who has an idea of what we should look at next? Well, we know R. We know how to find R.
Is R just that full distance in between the two?
It's 2 times 78 centimeters times the cosine of 26 degrees. Q, that's charge in coulombs. Yeah. We know there's a tension in that wire, right? Do we have any way to find the magnitude of that tension? We know that gravity is pulling down, and the Coulomb force is pushing out. How is gravity contributing to the forces on this? Yep. So, what does that force have to be for gravity to not pull it down any further? Well, not really. See if we can draw this more clearly. This ball is experiencing 2 forces. One that way and one that way. Okay, so that means that the net tension here is this way. Okay. Now y'all are making me think about this too hard. The gravity is pulling down and tending to pull it back in this direction. How hard is gravity pulling it back in this direction? This force times the sine of this angle is tending to pull it back in this direction. Everybody see that? Uh-oh. Somebody's got to change their answer. Now, the fact that that component of gravity pulling back in this direction is offset by this component, that's what has to be equal and opposite. That's where it reaches equilibrium. Of course, you're going to have the same on this side. Hmm? Now, is everybody seeing how this is resolved? Any questions? Any other, what about other problems? Any questions about other problems that you worked on? 15? Okay. And here we have each corner of a square. Now, since I put his in front of you, I'm going to put yours in front of him so he can see yours better and you can see his. We have a square with 4 charges. And the 4 charges are Q, 2Q, 3Q, and 4Q clockwise. Separated by one length, by the length L. Now what you want to solve for is the magnitude and direction of the force on charge 2Q. Okay? So on this Q, you have this force from, we'll call this Q1, Q2, Q3, and Q4, each of magnitude 1Q, 2Q, 3Q, and 4Q respectively. So don't confuse the index with the coefficient of the charge. This force is the force from Q1 to Q2. These are all like charges, right? They're all either positive or negative. So they're all repulsive forces. Here you have this force vector, that is the force from Q3 to Q2. And here you have a force between Q4 and Q2. And so what then is the net force on this charge Q2? It's the vector sum of these 3 forces. And do you see now how to solve it? You're going to have to calculate this distance, which will be length 4 to 2, which will be the square root of L squared plus L squared, or okay, the other lengths are just L. And that tells you that this force, this one is going to be K times Q times 2Q, 2 times 4Q, which is 4. Again, I'm sorry about this. Do not let the index of which Q we're talking about confuse you about the coefficient of how many times, the magnitude of that charge. And then divided by the square root of 2 times L squared. That gives you the magnitude of this vector, of that force. But it is at what? This is a square, so it's at 45 degrees. Okay? Does anyone know how to add vectors? Everybody here knows how to add vectors? Or have y'all done that? Okay, so you can convert between polar and rectangular coordinates and add them. And okay, seriously, if anyone doesn't know how to convert and add, and you multiply and divide them in polar, you add them in rectangular. Okay, good enough, as long as everybody knows it. You calculate the magnitude, you've got the directions. Add the 3 vectors together. That's the solution to the problem. Okay? Now, are there any more homework problems that you want to ask about? Oh yeah, I will always accept late homework assignments. It may cost you a few points, but A, it's a small number of points. There's 7 points for each homework assignment, so if you lose a point or two, it's better than losing all 7. Also, I don't know if you weren't here, you also need to know that over the course of the semester, each week, you can earn up to 2 points of bonus points. I'll keep track of them off books, and I will add them to your grade at the end of the semester if you need them. Okay? The way you earn the bonus points is each week you pick, at your choice, any additional problem from the homework problems and work it after you've done the others. This is, you can't do that instead of the assigned ones, but once you've done the assigned ones, pick another one, do it, you get a couple of bonus points. The end of the semester, that's potentially 30 bonus points, which can make a difference between, not quite getting from that B to that A and getting the A. What you can't do is wait until the last week and say, oh, I'm so close, what can I do to earn bonus points? At that point, the question will be, what could you have done, past tense? One more housekeeping point I want to make to y'all. This is important. I don't know how they do it in your other classes. I don't really care. I could care less how well you can memorize anything. In fact, if you observe me over the course of the next 15 weeks, you're going to find that I have a horrid memory. Okay? I don't remember numbers and formulas and equations. I just don't. So I don't care if you can memorize this form of Coulomb's law, or that K is equal to, what was it, 1 over 4 pi epsilon sub naught? Something like that. Look it up if you want to make sure. Definitely don't trust my memory for that. Okay? I'm bringing this up to tell you this. When it comes time for exams, you may have a 4x5 index card, just a standard index card. You can put whatever formulas or definitions or any of the reference resource material you might need to pass the test. You can put on that card, front and back. If you can write little bitty tiny letters and have a microscope or a magnifier to read it, knock yourself out. It's the same principle as with the homework. Show your work. I don't care that you got the right answer. I want to know that you knew what you were doing when you got it. Like I said last time, you can tell me that 2 plus 2 is 4 and still be wrong if you think it had anything to do with purple. Okay, so I want to know what you were thinking, why you did what you did to get the solution you got. And if you happen to mistype a number in your calculator and get an arithmetic error snuck in there somewhere, that's bad, but it's not going to be the end all and be all of the problem. Earn the points by showing me you know what you're doing. And then we'll worry about the. You still want to get the arithmetic right because that is important, but it's not the most important. Okay. Any more questions on homework before we hit 16.6? Okay, and just to satisfy my curiosity, would y'all confirm for me that the page numbers in my book correspond with the page numbers in your book? Were the homework assignment problems on the right page number in your books? And 16.6 is on page 450? Okay, good enough. And we covered 16.6 last time. We're going to 16.7. Thought that looked more. I thought that didn't look right. Told you I have a lousy memory. Y'all got to have to keep me on my toes. Introduced this course last week by pointing out to you that we were now going to be working, unlike Physics 1, we worked with mechanical forces. This time we're going to be working with field forces. And though I did not say so explicitly, I almost immediately showed you that that wasn't exactly true. What's wrong with that statement? Last semester, Physics 1 was about mechanical forces. This semester, we're going to start looking at field forces. Didn't you study gravity? Whatever the constant is of M1. Yeah, that's right. M1, M2 divided by R squared, the inverse R squared law. Gravity is a force that acts at a distance. And in fact, it looks, except it uses a different coefficient, constant coefficient, and it uses mass instead of charge. Otherwise, it looks exactly like Coulomb. Newton's universal gravitation law looks exactly like Coulomb's law. Now here is where it's going to get kind of warm and fuzzy. Let's get rid of gravity because for some reason we don't think about gravity this way. We just think of gravity as a force that pervades everything. But there's one fundamental difference between gravity, force due to gravity, and the force of electrical charge, and that is the introduction of those algebraic signs, positive and negative. You have two different kinds of charge. You only have one kind of mass, and it's all attractive. All mass attracts all other mass. An electric charge will either attract or repel based on the signs, the algebraic signs of the Coulomb charge, the charges involved. When we talk about the force exerted by an electric charge on another electric charge, we talk about something called the electric field. And we talk about field lines. These field lines that we're talking about are an abstraction that we visualize in order to keep straight in our mind what's going on. You have a charge, a little positive charge. Now wait, I want to make sure I use the same convention they're using here. Yeah. We're going to envision lines of force emanating from this charge. These lines are an abstraction. Okay, it's just something we make up to visualize. If we tried to draw an actual line for every line emanating from that charge, we'd just end up with a solid purple board because there's an infinite number of lines emanating. Okay, the question is, how strong are those lines? Well, we know that electric field, which it's a vector field, and we know that it is going to exert a force on that charge, on a charge Q that's placed anywhere in that field. So if we've got a positive charge here, exerting, generating this field of force lines, and we take another charged particle, another point charge, and we stick it in this field right here, the lines of force emanating from this charge is going to exert a force, if it's positive, and this one's positive, my stupid marker is going to start erasing itself, then it's going to exert a Coulomb force in that direction on that other particle. Algebraically, if you look at it in the book, you're going to see that they talk about the E field is defined as the force on the particle divided by the charge, the point charge, the test charge that's put there. Then they're going to talk about, if you read the book, they're going to talk about there's some assumptions that we're making, that this charge is small enough compared to the one that's producing the field, that it's not going to appreciably change anything. Okay? Everybody, show of hands again. How many of you have had algebra? I mean, not algebra. What am I saying? Calculus. How many? Everybody. Okay, cool. Then this is going to make a lot more sense to you than it might have. What we're actually going to do is define this in the limit that Q approaches 0. Okay? So if we could actually take and measure electric field lines, which you're going to see when we do the lab on this, that we can't actually measure the E field lines, and so we're going to cheat. Well, don't worry about it. We're not going to get ahead of ourselves. But if you could do this experimentally, you could start with a large charge generating the field and a small test charge and measure the force that's exerted on it and graph that, and then make the charge even smaller and graph that, and then keep making that charge smaller and smaller and smaller, and then extrapolate as you go to 0. Where does that, you would see that force asymptotically approaches some value in the limit that charge goes to 0. That is the force we're describing with that equation. Does that make sense to everybody? I mean, okay. Because it really can mess with you. This messed with my mind when I was an undergraduate and taking electric E&M the first time. Like, but how can you measure the force on something that's exerting a force on what it's being made? You put it in there, you're going to change things. Of course, when I did this course, I hadn't yet had calculus, so the idea of taking something in the limit hadn't been introduced yet. So maybe I was worried about nothing. Now, let's go through this, because we know what this force is. We know that the force exerted on this particle by this particle from Coulomb's law is equal to K, Q1, Q2, over R squared. And that means we can set this equal to the electric field times the charge, the test charge, Q, which I need to be consistent. So we're going to call this charge uppercase Q and this charge lowercase q. Now that ain't going to happen again, at least not today. Next time I'll probably forget it in my pocket again. But okay. Well, let's solve this equation for E. Take K, Q divided by R squared, and divide both sides by Q, and we end up with E. The E field is equal to K Q over R squared. And we should also remember that we can change K into 1 over 4 pi epsilon sub naught. And that is the equation of your E field. Is it? What's wrong here? What do I need to do to fix this? No, the q, the lowercase q canceled out. So it's no longer an influence in this equation. But what is wrong with this equation? Say again? Well, let's see. We know we've got coulombs. And we've got divided by meters squared. What's the, 4 pi is unitless. What's the units of epsilon sub naught? Yeah, I would have to go back and look. Okay, the point is, you have to work out the units of epsilon sub naught, but at the end of the day, it's going to end up into, I want to say newtons per coulomb. Yeah, newtons per coulomb, where newtons are defined as meters per second, or kilogram meters per second squared. So, yeah, it's actually part of the units. Newtons per coulomb. And you could use that as a way of working out the units of epsilon sub naught if you wanted to, or you could just look them up. But the units here are not the problem. The units are right. The electric field has units of newtons per coulomb. That's what we end up with when we do that algebra. But E is a vector. The electric field, E field, is a vector field. What part of this is a vector? None of it. This is a scalar quantity. So to make this equation correct, we need to put the absolute value lines. Talk about the magnitude of the electric field as being equal to this.
But the equation above it's okay, right? Or should it be that before?
Well, it should have them.
Okay.
Absolutely. Same here. Yeah, but this is the point. The E field is a vector field. So when you start talking about the magnitude of the E field, it's important to remember that this equation will give you the magnitude. It'll give you the strength of the field at any point, but it doesn't tell you anything about the direction. You have to treat the direction separately. Now, if you know it comes right back here. See, at this point, the force that's being exerted is a vector. And so the force at the point where Q exists is equal to that E field times the scalar quantity Q. Now here in this first example they talk about E at a point between two charges. We have a charge here, you have a charge here, and on a line connecting them at some random point, what is the E field there? Well, you can write this as a vector because you've only got two point charges, and so you know that the force, if they're both the same, is going to be repulsive. If one is positive and the other is negative, then you'll have the direction. But you have to know the sign of the charges in order to talk about the direction. You don't have to know the sign of the charges to talk about the magnitude. Well, actually, you might still need that, because if the magnitudes add, then that's going to be one result, and if they oppose, that would be a different result. So and even then, you're going to need the vector quantities to do the addition. We can go ahead and start on this next section, talking about the idea of field lines. There's a couple of, again, this is kind of arbitrary. It's just the way, thank Ben Franklin for assigning the algebraic symbols, plus and negative. If you have a positive charge, then the standard is that the field lines emanate away from the positive charge. And you would draw them as straight line segments, indicating that they don't end. And instead of putting the arrowhead on the end of it, which would make it a vector of definite length, you put the arrow just somewhere in the middle of the line to show direction. Because these lines, these E-field lines, extend infinitely in all directions. Now, you get far enough away, they get weak. They get very weak very quickly. It's an R-squared law. But they don't actually end anywhere. That's a positive charge. If you have a negative charge, they generate the same lines, but this time the lines point towards the charge. So that if you start talking about two charges together, in this case, the lines are going to emanate from the positive and come over and join to the negative. Even from way around here. Okay. That becomes what would be a dipole. We'll get to that in time. What if both of your particles were the same charge? See if we can do this a little more neatly. And you know what? What if this is also a positive charge? Well, now the lines are going to diverge from each other. These are force vectors, not E-field lines. This is a force vector. This is, yes, and that's exactly what would happen. These field lines, think of them, imagine, visualize it like magnetic field lines. Because they're fully, completely analogous. If you have two north poles and you're bringing them together, the field lines are going to billow out from each other like that, and that's going to push away. That's going to push them apart. If they're different, if this is north and this is south, then the lines are going to go from positive to north to south, maybe, The lines are going to join the two and draw them together, try to pull them in. But these are not force vectors. These are field lines. And they're actually just a representative subset of the field lines as they would exist. Because, like I said, if you tried to draw all of them, you just black out the board. And they've drawn some examples for you here on page 458 that are pretty good and give you a good idea of how it all works. And they're going to work up to, of course we're not there yet, but we're going to be working up to a point where we're talking about conductors near each other with the charge distributed over the surface of the conductor, which we're going to talk about in another class. Suppose you had a conductive plate that was covered with positive charges all over the surface. And here next to it, and another plate was covered with negative charges. Now you're going to see some fringing effects out here at the edge. Again here. But by and large, all of the lines, the E field lines between these two conductors are going to be homogeneous, straight, uniform lines. How do you imagine they would change if the conductors were both covered with positive charges? They would just billow away from each other. On both sides. Hope I didn't bore him. Are there any more questions? Anybody?
Does it ever get to, like, say, if the magnet would be curved there, all the lines would be straight? Did it ever get to that in the book?
Okay. First of all, this is not magnet. This is electric field. But no, what we're going to get to, what we're going to learn when we get to it in the book is that the electric field emanating from a charged surface will always be normal to the surface, perpendicular. Okay? If the surface is curved, then it will be normal at all points, but that means that the field will actually be fanning out. Any other question? Everybody's happy? Okay. Everybody has been able to get online, see the online classroom. You see where to find the assignments for homework. Okay. We'll address any homework questions when you come back. Everybody has signed the attendance sheet, turned in this week's homework.
Is that all you want?
That'll work. I think so. That's your name, class. Got it. Excellent. Thank you. Now I'll go see who it was that thought they were important enough to interrupt my class.
Yeah, I'm not seeing anything. Am I D2L here for physics and the content? Is it under discussions or anything else? Or?
Okay. Let me see your phone here. All right. Oh, wait a minute.
You have to go to Geese right now for PLC?
You got like a 45-minute break. After that class, we go to PLC like 5 minutes.
Gosh. So I'll have to sign in there. Okay.
Yeah.
Got it. Thank you.
Yeah.
My name's Dylan.
Joe,
Nice to meet you.
Dr. Abear.
What do you, Dr. Avery? That's what you like to go by?
Please.
Okay. I didn't get that homework assignment done. I can give it to you Wednesday.
That's
Is that
fine.
okay?
Yeah. Late
You
is
said all
late
the
is
time-
better than never.
Okay. It's always going to be posted on D2L.
Yeah.
And it's going to be Monday. It's posted.
It'll be there. It may show up earlier than that. I don't.
Okay.
It should have shown up by Monday, and then it'll be due a week later.
And then it's always due on Monday.
Always due on Monday. And late is better than never. So. You too. Yeah, I need to.